Today we want to look at polar coordinates, which is just another description of R2, two-dimensional space. And it's just another set of coordinates. Now, the reason that we want to do this is that, first of all, this is something that we do. And second of all, we spent the last 2 days describing something that was very, very round with very, very square coordinates. And it became very, very messy. There was trigonometric substitution involved. Anytime that shows up, we should stop and say, hey, is there something else that we could be doing here? Because, whoa. So polar coordinates is just another description of R2. This is going to be very good at describing things that are round. That's why we did this. So the reason I want to start with polar coordinates, especially on a Friday, is because that we might be familiar with polar coordinates. You see polar coordinates when you're in trig. You see polar coordinates in pre-calculus. You see polar coordinates in Calc 1 and Calc 2. You might not have spent a lot of time analyzing things in polar coordinates. And like at the beginning of the class, I immediately went back to rectangular coordinates because we're most familiar with that. So if we have two-dimensional space and our standard representation is x-axis, y-axis, and points in this space have an x-coordinate and a y-coordinate. So we say that that point is x units away from the origin horizontally and y units away from the origin vertically. So this point is described with two distances. Distance from the origin and a distance from the origin. So we have two distances, one horizontal, one vertical. This is the rectangular coordinates that we're first introduced to. This is the first way that we describe R2, with a horizontal distance and a vertical distance. But there's another way that we can describe this particular location. So we could say that this particular location, we can describe that with one distance which we're going to call R, and then some kind of angle. So instead of saying go 3 steps to the right and 5 steps up, or 4 steps up, go 5 steps at an angle of 37 degrees. So we describe this point with a distance, one distance, and an angle, a direction. So we might say this point has coordinates r, theta. It's r units from the origin through an angle of theta degrees. Now we have to have a 0 angle, and that's going to be at the positive x-axis. So right now, we're learning polar coordinates in terms of rectangular coordinates. But we're describing this with a single distance. And then an angle. So 0, 0 is our rectangular coordinates for the origin. Zero, 0 will also be the coordinates in polar coordinates, but we're going to refer to that as the pole. In polar coordinates, we'll refer to the origin as the pole, except for the fact that that was probably the last time I will refer to that as the pole and just go back to saying origin. In terms of rectangular coordinates, when we define where the location of the pole, we have to define a 0-degree angle or a 0 radian angle. So the pole is not just the point, but it's also, in this case, a ray coming out in the direction of the positive x-axis. So that is part of the pole. We have to decide where 0 degrees is. So here's 0 distance. Here is 0 degrees. In many semesters, I just go with 0 radians all the time. I bring up degrees because I have a trig class this semester, so I'm thinking in degrees again. So that's just the way it goes. There's a bunch of semesters where I didn't have trigonometry and I completely switched over to radians. I'll be like doing stuff at the house. I'm like, all right, I need to make a pi over 2 angle. People are like, oh wait, what are you talking about? I need to make a pi over 2. I need to make and then I went into my menu in my brain and so switch back to radians. I need to make a right angle. I went directly to the word right angle because my friends didn't know what 90 degrees was either. So we've changed how we're describing this location. Now, these coordinate systems are, of course, related. Notice that I've got a right triangle here. So we can see that x squared plus y squared is equal to r squared. That's a relationship. If I want to know what r is, I have a relationship between x, y, and r. So I can say x squared plus y squared is equal to r squared. If I want to know what the angle is, the angle also involves x and y through the tangent. The tangent of theta is y over x. So if I want r, I could just square root x squared plus y squared. And if I want theta, I could just tangent inverse y over x, and then be conscious of what quadrants we are in. The y and x signs will tell us what quadrant we're in. Notice that when we invert tangent, we're only going to get angles in the first and fourth quadrants. So if we're in the second or third quadrants, we just have to be aware of that and know that we're going to be getting a reference angle. So if we tangent inverse, make sure that we are aware of the quadrants. You'll know what quadrant you're in because you know what y and x. If you're doing tangent inverse of y over x, you know what quadrant you're in. So just make sure that you remember that tangent inverse only returns values from Q1 and Q4. So if you're in Q2 or Q3, you got to move things over. We can also do our favorite and figure out what x and y are in terms of r and theta. So here's r and theta in terms of x and y. We can go back and say x is r cosine theta because dot product or horizontal and vertical components, and y is r sine theta, horizontal and vertical components. Polar coordinates are going to be very good at describing things that are round and very bad at describing things that are rectangular. So here is the description we have for a circle of radius 5 centered at the origin in rectangular coordinates. We had to go up to quadratic. X squared plus y squared equals 5 squared. In polar coordinates, here's the description. The radius is 5. The radius is 5. So the description in polar coordinates a constant function is a circle. Polar coordinates, our constant function is a circle. In polar coordinates, r equals a constant is a circle. The equation r equals some constant is a circle. That's an improper use of a comma. Don't add them. I know. So polar coordinates are going to be very good at describing things like circles, because we could just use a constant function to describe a circle. In rectangular coordinates, constant functions describe horizontal and vertical lines. So in rectangular coordinates, constant functions describe vertical and horizontal lines. In rectangular coordinates, our constant functions are going to be horizontal and vertical lines. Like y equals a constant, it's a horizontal line where y is 5. X equals constant is a vertical line. I said 5 and constant before. In rectangle, I'll edit that out. Actually, I won't edit that out at all. I like to leave the mistakes in. In rectangular coordinates, y equals 5 is a horizontal line where y is 5 all the time. X equals -2 is a vertical line where the x coordinate is always -2. So our constant functions in rectangular coordinates are horizontal and vertical lines. I realize I said a vertical line was a function. If we write x as a function of y, then the vertical line test becomes the horizontal line test. So once again, don't at me, comments are off anyway. So let's take a look at another constant function. I brought up constant functions. What if I have, let's say, theta equals a constant? So we're going to go to an angle of theta equals pi over 4 and plot every value of r. We're going to go to a line theta equals pi over 4. Or sorry, we're going to go to, I just gave it away. Because I said it's a line. But it's specifically, it's a line through the order. So I'm going to go to theta equals pi over 4, and I'm going to plot a radius of 0. That's not helpful. But then a radius of 1 at an angle of pi over 4, and then a radius of 2, and then a radius of 3, and then a radius of -1, and then a radius of -2. And right now, things are getting very suspicious. You're like, oh, whoa, 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 that's the origin. Isn't that 0, 0? I go, yeah, it's also 0 pi over 4. Things are weird when we start throwing angles in there. This point is, say, 1, a radius of 1 at an angle of pi over 4. This point here is a radius of 2 at an angle of pi over 4. Down here, we have a radius of negative 1 at an angle of pi over 4. Face in the direction of pi over 4 radians and take one step backwards. So here at theta equals pi over 4, we're getting a line through the origin with a slope of 1. We're getting a line, specifically a line through the origin because of the radius of 0 thing. Let's look at how theta relates with x and y. Notice that tangent of theta is equal to y over x. So if I look at tangent of theta is equal to y over x. And if I drop the theta, since theta is constant, I can just replace the theta with pi over 4. Tangent of pi over 4 is y over x. But tangent of pi over 4 is equal to 1. So the equation we're looking at is y equals x. I multiply both sides by x. And y equals x is a line through the origin. With a slope of 1. We wouldn't describe the slope of the line when we're talking in polar coordinates. Slope is change in y divided by change in x. In polar coordinates, there is no y in x. And it would be crazy to say line through the origin at an angle of pi over 4. That's like just the description. But we know we've made this connection, line through the origin with a slope of 1. That's a little translation for our friends who are still thinking in terms of rectangular coordinates. So the cool thing is, so now that we've seen what our r equals constant and theta equals constant look like, so just different values of theta will change the angle of our line. So theta equals pi over 6 will be an angle at a 30-degree angle. Pi over 3, pi over 2 would be this vertical line through the origin. The important thing to remember is that theta equals constant is going to give you a line through the origin. R equals constant is going to give you a circle centered at the origin. So this gives us some different looking graph paper in polar coordinates. Graph paper is what old people call it. It would be the grid setting on your tablet. I gotta update my shit, man. I think the first time you were able to put a grid on some notes that you could write on a computer, they probably called it graph paper. And someone's like, oh, what the hell, man? This isn't paper. And they're like, oh, shit, but we've always called it graph paper when we were playing Dungeons and Dragons. And now we need a grid. Just call it a grid. So, all right, grid. Are we going to start calling it grid paper? No. That's still going to be graph paper. And then the pedantic bastard in the corner is like, well, you can make a graph just on regular lined paper or even blank paper. And then they're going to be like, oh, shut up, Leech. Oh, wait, I'm not the pedantic one in this scenario. Spoiler alert. Or actually, I need Morgan Freeman to do a voiceover. It turns out he was the pedantic one. So we're going to get a different looking grid because the grid on graph paper, on the grid setting, is just all your constant values. X equals 0, X equals 1, X equals 2, X equals 3, Y equals 0, Y equals 1, Y equals 2, Y equals 3. So your grid looks very different because your grid is made up of constants. The grid is all the constant values. On your graph paper, the grid is constant values. That's why we have all those little squares on rectangular coordinate graph paper. But here, our grids are now lines through the origin and circles centered at the origin. I keep saying origin at the pole. I'm just going to say origin. So we'll have some origin on our graph paper, and we'll have a bunch of circles, concentric circles. For r equals 1, r equals 2, r equals 3. Can I do another one? Kinda. One set of lines on your paper are concentric circles. The other set of lines are going to be theta equals 0. Theta equals pi over 2. Theta equals pi over 4. Theta equals 3 pi over 4. Theta equals 4 pi over 4. 5 pi over 4. And 6 pi over 4. 7 pi over 4. And 8 pi over 4. And 9 pi over 4. And 10 pi over 4. And 11 pi over 4. And 12 pi over 4. Polar coordinates are weird because we have an infinite number of description for any given point. We're going to be one fixed distance away from the origin. Unless someone is facing in the opposite direction, then we're negative that distance, but that's really easy to predict. But we're also, wherever we're standing, whatever angle we use to get there, plus or minus 2 pi will get us to the same location. Using angles in your description can get a little weird. Because here's where 0 is, but it's also where 2 pi is. So that means it's also where 4 pi is. I spelled 4 pi wrong. Ugh, what an awful way to spell 4 pi. And also 6 pi, and so on. And also before that, negative 2 pi. If we get to pick what angle, pick the one between 0 and 2 pi. But if someone comes along and says 4 pi, translate that to 2 pi. So remember, when you make graph paper, that's just where the constants are. That's what your reference is. And here, our constant functions are lines through the origin at a given angle, so sweeping around, and concentric circles. That's what your graph paper looks like in polar coordinates. We went through multiples of pi, fraction multiples of pi, because it's more convenient than making angles at 0, 1, 2, 3, 4, 5, and 6. Because 0 is also the same location as 6.28. So that's kind of inconvenient. So multiples of pi are the way like I was there. Our normal graph paper is the same thing. All the x constants, here's where x is constant, 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 y 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 is constant. Grids just show you where your variables are constants, fixed value of your variable, of your coordinate. How's everybody okay? It's most likely that you've seen this before. These are your core principles of polar coordinates. How to define the polar coordinates. What's the point of polar coordinates? The point is a distance and an angle. What are the, is this related to rectangular coordinates? Yeah, here's how we relate them to the rectangular coordinates we're familiar with. Here's our translation between the two. What do our constants look like? This is the other thing that we need to look at. What's our graph, which is the same question as, what's our graph paper going to look like with these new coordinates? And there's our graph paper. So the question is like, oh, dude, we're in Calc 3. This seems like some old stuff that we're supposed to know. So I'm pretending like I know this already. It's like, oh, why are you telling me stuff that I already know? I'm like, well, because there's a quiz. I want to make sure you do okay. It's like, oh, I gotta go because I got a thing. I'm just kidding. There's no quiz. Oh, my thing just got canceled. We're good. All right. Because I like to remind you of things that may or may not have gone before. How is this relevant to our interests? So how is this relevant to our Calc 3 stuff? If you recall, if you would recall, when we're describing round things in rectangular coordinate, that's a bad fit, round and rectangular. I know there's that video where it's like, oh, where's the circle go? It goes in the square hole, right? I don't know if you've seen that one. But describe in general, when we actually need to analyze things, trying to describe round stuff with rectangular coordinates is a bad fit. Especially when you're looking at things close enough or far enough away that how round it is matters. Like it doesn't, we could put a grid on most places on the earth, even though the earth is kind of round, because we're looking really close and it looks flat. So that it's fine. It's fine. But things would get really messy if we try to put a rectangular grid on a much smaller thing. Try to put 1-inch squares onto a basketball, and all of a sudden, it don't look so flat anymore, right? If I take 1-inch squares and put them on the face of the earth, the curvature of the earth is not really going to be that relevant, at least in a very large area around where any human being might be standing. Like if I take that and I try to wrap it around the earth, it's 1-inch squares. There's going to be a place where it doesn't line up properly, right? It's like why mathematically you have to have the palette somewhere on your head. Right? So somewhere your hair is going to have to go. It's like, oh, now we can't all go in the same direction. And it's going to go back, you know, how hair does. I had one of those. My hair, when I was a kid, just stuck up straight up in the back. I had like a fan in the back of my head. And there was nothing to do about it. Except for the fact that I used to like to wear a picture on my head. So it was perfect. I think that was my little kid solution. My baby solutions, I saw like this picture. It was like one of those big pictures with a little spout and a plastic handle and it graduated on the side. And I was like, oh, hat. And my mom was like, "Oh, not a hat." Took it away. I was like, "Oh, I think you're wrong about that. Fucking hat." I swore a lot when I was a kid. We're describing a round thing with rectangular coordinates. That's messy. But if we have this, so this is a function of x and y. We're going to want to trade this for some function of r and theta. Because we're describing a round thing with square coordinates. We were describing a round thing with square coordinates. That means things are going to get messy. In particular, this led to trig substitution. And even though trig substitution is our favorite, and we love any opportunity to do trigonometric substitution, maybe there's a better way. The other reason that we would want to do this is because we can, and that's what we're here for. We're here to learn the things that we can do. Here was our function in terms of x and y. But we remember x squared plus y squared is a circle. And also x squared plus y squared is equal to r squared. So just replace the circle with r squared. That's just mechanical. On the previous page, we wrote r squared equals x squared plus y squared because Pythagorean theorem. We just take the x squared plus y squared and replace it with r squared. Now, we do end up with a little bit of a problem here, dx and dy. The problem is this, dx and dy are both distances. Dx is a small piece of x, which is just a small piece of a distance. Dy is a small piece of y, which is a small piece of distance. The problem that we run into on this end is that r is a distance. So dr is a distance, but d theta is not a distance. It's a small change in an angle. It doesn't have units. It's got radians, just not units. dr is a distance. We could use it in dA, our area. Remember, dx, dy, and dA is the area. So dr is a distance. We can use it. That's not the problem. That's awesome. But d theta is an angle, not distance. Now we have a problem. I can't just replace dA with dr d theta because d theta isn't the distance. So all we have to do is figure out how to make dr d theta into an area. And that's just turn d theta into a distance. So how do we turn d theta into a distance? We need to turn d theta into distance. We need to make d theta a length, something in meters, or foot, or inches, centimeters. Once we get that, that'll make the rest of Calc 3 super easy. Once we see how we turn d theta into a distance, that'll make Calc 3 super easy. And I'll be like, hey, cylindrical coordinates, polar plus z. And you'll be like, oh, got it. And I'll be like, oh, spherical coordinates, just one distance and two angles. And you'll be like, oh, got it. And everything will make perfect sense. But I got to do it right now, like on the same day that you introduce the idea of polar coordinates. If you don't do it right away, then it's just ruined. You have to do work. We all know that we want to try to avoid work. So here's how we turn d theta into a distance or a length so that we can immediately understand the rest of Calc 3. So here we go. If I don't do this now, we're not going to get it. So what we need to do is, oh, look at the time. That's going to do it for today. That's going to do it for this week. I will see y'all on Monday. Everybody have a good weekend. Thanks for playing. And thanks for coming in person and online. I appreciate you all.